Okay, hello everyone. So this is going to be a short walkthrough video on a airfoil, not the airfoil that you have due for what is it, a week or a couple weeks in spring 2024, but an airfoil. So, couple things. This topic has come up before, so I've just made an empty file and saved it. When you're opening a file, don't go to the desktop and double click on it. That is not going to work. Instead, you need to open the software like you would make a new file. Actually, hold on a second. There we go. Highlight my mouse so you can see a little bit better. Excuse me. You open the software, blank window, as if you're about to make a new simulation, but instead you can do file load or the load button on the top left here. It will pop up. Hold on a second. You can't see that. It's on the other monitor. There we go. It will pop up a box that looks like this. This is identical in every way but one to the dialog box to create a new file. The addition is it has a file entry right here. And this is where you can select the file to load. So AE169 NACA 4412 is a simulation file I just named a little while ago, and we can load that one. We can't load it with this POD key. I don't want to put the POD key in the video because otherwise it shows up on the internet. So this one is currently invalid. But I think off screen-ish, I should... I'm going to pause this for a second, but we're going to go ahead and put in a proper POD key and open the simulation. Okay, so the simulation is opening with a valid POD key this time. I'm specifically running this with 14 processor or processing threads, but you should be using however many as you have available, -1 or 2 depending, for the operating system. And we'll let this eventually get around to figuring out what it wants to do here. Right, okay. So it's fully open. This is a file. This is not a new file. This is one I saved previously. It has nothing in it, but it's a loaded file. And we had to load it from within the software. So, how do we go about importing geometry that we're not making natively inside of StarCCM+? We can go up to File and Import. And we can import a volume mesh if we had one. Some computer-aided engineering models we can import directly. Other things like that we can do. We can import a CAD model into 3D CAD. We can also import a surface mesh. So we're going to, at least, to be perfectly honest, I haven't used the import CAD model into 3D CAD before. We'll give that one a go and see if we can make this work here. So, let's see here. I believe this is saved. I guess let me just copy it over to the desktop real fast. There we go. Okay, so there we go. So the NACA 4412 2mm rounded trailing edge. You can click open, and it pops open this in the 3D CAD level. So this is one way we could do this. We can manipulate this part on 3D CAD. We could do extrudes, cuts. We could do all kinds of transformations. Anything we can do in 3D CAD within StarCCM+, we can now do to this part. Now, this is an airfoil already. We shouldn't need to do anything special to this. So while we could absolutely manipulate this on the 3D CAD level, we don't really need to. So I'm going to close 3D CAD. and show you and delete this, and also show you the other way to do it, which is the way I would typically do it for something like this. It's not the only way, but it's certainly the way I'm more familiar with, which is import surface mesh. So again, we look at the NACA 4412, 2-meter trailing edge, and it pops up a dialog box that looks like this. So by default, most of these are pretty okay. You might need to mark all CAD edges if you need some edges to be highlighted that aren't. But the thing I would select, which doesn't matter a huge amount for this case, but might for others, is create one part surface per part. If you don't do that, then you could wind up with a really long list of surfaces that is not particularly useful. So create one part surface per part is checked. You can click OK. And we have a geometry scene with our airfoil. Well, how big is this airfoil? That's a good question. I happen to know pretty much how big it is because I made the CAD model for it. But if you don't know, you can find out in Story CCM Plus pretty easily. Up here, there's a ruler icon. It's right next to a little yellow angled rectangle sort of thing and a grid. If you mouse over it, it says measure distance. You can click on that. And you can click, it will highlight the little ruler icon, and you can click on any 2 points to measure the distance between them. It can get a little bit finicky because it's trying to measure in 3-dimensional space. You notice if I move the mouse just a little bit, it says over 5 meters. Whereas if I put my mouse barely on the back of the airfoil, it says about 2 meters. So this is maybe ever so slightly greater than 2 meters in chord. According to this, 2.002 meters, but I might have not clicked on the leading edge perfectly. So it's very slightly over 2 meters in chord length. 2.005 looks to be it. So this is slightly over 2 meters in chord length, not the airfoil you have for your assignment. I want to emphasize that. This is bigger than that airfoil for starters, and it's not the same shape. But it is an airfoil. So this is our airfoil shape. We have to go from here and we have to create an air domain around this airfoil. For this, we need to actually create the volume that will make the domain. So I'm going to go to Parts, New Shape Part, Block, and we will create a block that will be the domain of air around this airfoil. So the leading edge of this airfoil so happens to start at pretty much exactly 0, 0, 0. Yep, the leading edge is indeed 0, 0, 0, or very, very, very close to it. So what we're going to do here is we are going to go, let's see here, the airfoil's 2 meters chord. So we're going to go 10 meters upstream. That's negative x 10 meters. We're going to, and that's 5 chords. We're going to go, I want to say 15 chords downstream, so that's actually 17 times 2, so 34 meters downstream. Because we have 2 meters for the chord, and then another, but that'd be 32 meters downstream, not 34. 2 meters downstream to get to the back of the airfoil, and then another 15 times 2 downstream to get to the 15 chord lengths downstream. And 15 honestly might be a little bit low, like 42 might be slightly better. It depends. Really, we would have to see the results of the simulation to know for sure, but it's probably somewhere up in this neighborhood is appropriate. We're going to go 10 meters, and we don't know exactly how thick the airfoil is. I mean, it's a 4412, so that actually tells us, I believe, that it's 12% thick. I'm here 12%, so it's approximately a 1/4 meter thick. we're not going to worry about that too much. We're going to go 10 meters up and 10 meters down. And we're going to do a two-dimensional simulation. So we're only going to go 2 meters out of plane. We don't need to go any more than that. So this is going to be our air domain. I'm going to click create, and I did click create, but it didn't close the dialog. There is still a block though. You can create more than one of these if you wanted to. So we have a block, so I'm going to rename this block air. I'm going to do my best to follow best practices here, including naming things. But we'll see how that goes. And then we need to split this block into different surfaces. Right now, we have 6 faces, but they're all just one piece. So we're going to split by angle to get us 6 surfaces. We have the back surface, which is our outlet. We have the in-plane surface, which I'm going to just call in-plane. That is, should be our simulation domain. We have upper. We have our inlet. And we have our lower. And we have our out of plane. Okay. And also, our airfoil itself has a couple of different surfaces, even though it's not going to be stupendously obvious. So I'm going to split by patch. So what this is going to do is highlight different sections of the airfoil so we can separate them. So I'm going to just create the main body of the airfoil and just call it airfoil. And I'm going to select the rest of this and call it trailing edge. I'll get to why that's important in a little while here. For a sphere or any other uniform symmetric geometry, this wouldn't matter, but we will have to do some special treatment to the trailing edge because of how thin it is. So we have our airfoil and we have our air. Now we need to cut our airfoil away from the air. This is an operation. New, Boolean, subtract. Operation. For the Boolean operation, we select everything involved, the thing you are cutting away from and the thing you are using to cut. And then you select the target as the thing you want to remove material from. And we can go ahead and just have it do this immediately. Now we have a subtract. And it does indeed appear as if we have a hole all the way through. Now, it's possible that you might not have a hole all the way through. You might have a sliver of material left on one end. If that happens, you might need to shuffle this airfoil over a little bit before you subtract it. So, let me just demonstrate how that works really fast. If we wanted to move this airfoil over, this is a surface preparation transform operation. So if we want to move the airfoil over, we select the airfoil. And under transform, it doesn't do anything by default. It just says, hey, we're changing this in some way. You get a little folder, or you get a little node called transform, and then a little folder under that node called transforms, plural. If we right click on transforms, we can get new, and we have translate, rotate, scale, reflect, coordinate, and motion. We're just going to translate. We're going to translate it over a little bit. So there's a new translate node under the transforms folder. And we can tell it which direction we want to translate it in and by how much. In this case, I'm going to move it 1 meter, or -1 meter actually, in Z. Execute. We can see, if you were looking closely, it's shuffled over. Let me translate it by 2 and you can take a look again. So if I change that to 2 meters and hit execute again, we can see it moved over. Now, here's something that might be messing with you, or might be going to mess with you. These operations are order dependent. So right now, this subtract hasn't done anything different because it happened before we moved it. If we want to change the order, we can right-click on operations and say reorder. Get a dialog box that looks like this. We can move the transform in front of the subtract so it happens first. And hit execute. Now, before we subtracted it, it's transformed rather than the other way around. Now, this is a translation operation. These also incidentally happen in order, by the way, if we had more than one. And we will need to transform this airfoil in other ways, because we are going to want to know what happens as we change the angle of attack of this airfoil. So we need to be able to rotate it. I'm not actually rotating it right now, I'm just rotating the view. You can see the coordinate system rotate on the bottom left. But that's the concept. We want to be able to change the angle of attack. So, we're going to right-click on transforms, and you might have noticed there was a rotate option. We're going to use that. Rotate. And we are going to rotate about the z-axis. So, what we're actually going to do is rotate about negative z. Because a positive rotation around negative z will give us a positive angle of attack. If we just gave it a positive angle around z, then it would give us a negative angle of attack. Which is not what we want. So, I don't want 10 radians. Let's say 5 degrees. And we're going to execute. And we can see that this airfoil rotated slightly. I can grossly exaggerate this and say 50 degrees. Execute. And it rotated a lot. Notice the coordinate system didn't rotate, but the airfoil did. Let's put this back to 5. Okay. Now, it is currently rotating about the leading edge of the airfoil. The origin is 0, 0, 0. And it's rotating about that point. We could do that, but then we're moving every single point on this airfoil. Which isn't great. So what we're going to do, actually, is we're going to rotate about the quarter chord. So instead of rotating about 0, 0, 0, 1/4 of 2 meters is going to be half a meter. So we're going to rotate about half meter by 0 by 0. And this is going to rotate it about a slightly different point. Wait, did I plug that in properly? 0.5. Okay, let me grossly exaggerate this and say I'm going to rotate it about the trailing edge. Let's see here. A little bit hard to see, incidentally, so it's a little bit hard to sanity check. But I think it's doing what we want. So the other thing we can do here is we really want to verify this. Let's go ahead and put a cylinder, at least temporarily, located at 0.5. We'll only make it like 1 centimeter and maybe 5 centimeters. Great. And I'm going to add it to the scene. And call it C/4 reference. So theoretically, this is at the quarter chord. And I'm going to add it to this geometry scene so we can see it. There we go. Okay, so theoretically it should be rotating about that point. Let's rotate about the leading edge. And let's also rotate by more than 5 degrees. Let's rotate by 45 degrees to make it really obvious. Just make sure everything's working. Okay, yeah, it's not rotating about that. It rotated about the leading edge. Now let's plug in 0.5 space 0 space 0 and try that again. Hey, it rotated about the quarter chord. Because the cylinder didn't move, reference where it would be at 0 degrees angle of attack. Yeah, it's rotating about the quarter chord. And we can visually verify that. Okay, that's better. So now we can freely rotate the airfoil. If we want to get really fancy, we can also create a new coordinate system that would be anchored to the airfoil, but we're not going to worry about that for now. So we have our subtract. I'm going to rename it to something a little bit more appropriate, like domain. Air domain. Okay. And we can go ahead and create a region from this. Assign parts to regions. Get a dialog box. I want to create a region for all parts. Each part doesn't matter. There's only one of them. But create a boundary for each part's surface is the important part here. Click apply. We now have a region. You can see it shows up under air domain. And we have all of our boundaries. Oh, I skipped a step. I made this 3-dimensional, so I need to delete that. I apologize. So what we actually need to do is badge this for 2D meshing. You need to take our air domain and badge it for 2D meshing so that it properly recognizes the fact that it's going to be a 2D simulation. Now we can go assign parts to regions. Order of operations, very important. There we go. Okay, there we go. We still have boundaries. We have less boundaries, though. So we're going to have a velocity inlet. The top and bottom surface can be outlets, or pressure outlets, excuse me. The back can also be a pressure outlet, incidentally. And then the airfoil itself has a couple of walls on it. One for the bulk of the airfoil, one for the trailing edge. Notice that while we have the full span of airfoil here, our block's only 2 meters wide, so we only see part of it highlighted when we select the surface. Now we can mesh. So mesh, automated mesh, 2D. Well, we only have one 2-dimensional domain, so it makes this nice and easy. We can just select that. You could do a quadrilateral or triangular mesh, but for 2D, polygonal tends to work a lot better. For 3-dimension, I usually recommend a different form, which we'll talk about when we get there. So, again, the concept for meshing is we have default controls. This is what it will do if you don't tell it specifically to do something else. This is what it will do by default. So I'm going to give it a default cell size of, I'm going to go with 4 centimeters. So 50 cells across the length of this airfoil. The target size will be 100, so it will try and make cells up to 2 centimeters in size on any surface. It will make cells as small as, I'm going to say 5%, so that's 2 millimeters on any surface. If you're paying attention to the name of that file, you know that that's a problem, actually. We'll get to that in a minute here. Surface curvature, it's going to use 36 points to approximate a circle by default. I'm going to bump that up to 50. Surface proximity, this doesn't matter for our case because we don't have any parts that are near each other. But if we did, we could tell it, hey, try and put more cells in between surfaces that are close together. Surface growth rate, I'm going to want to turn this down to a user specified 5%, because even slow is too fast in my opinion. Prism layer total thickness, I usually find 33% is a little bit aggressive, so I'm going to bump it up to 50 and we'll see how that looks. And let's just tell it to mesh and see what happens and see what the problems are. Fortunately, this is 2D, so it's not going to take super long. I'm going to open a new mesh scene so we can take a look at this. Hey look, we have our mesh, we have our airfoil, but we've got some problems. So let's zoom in on a couple of these things. First up, we do not need cells that are this small all the way out at the perimeter. It made those small cells 2 centimeters to a cell all the way out here. We really don't need that. So let's go ahead and fix that. The way we do that is with a custom control. We can tell it on some surfaces, so we can control the behavior on surfaces. So I created a new surface control. We can tell it on several surfaces, including the inlet, the outlet, the lower surface, and the upper surface, do something different. And it even highlights the surfaces it's doing something different for. What do we want to do different? We want to change the target size. We want to change how big they are allowed to get. Honestly, everything else is probably fine. We just need to make the cells so they can grow bigger. So I'm going to say 800%. Easy enough. Let's just execute again, and we should see the cells get much bigger out here. Lo and behold, they are much bigger. That's probably about right, actually. So we fixed that part. But notice that the cells are also getting bigger in this gap behind the airfoil. They will just, if this were a hypothetically infinite plane, these would just grow exponentially, getting 5% bigger each time there was a new cell. That's not something we particularly want. We want to limit the maximum size anywhere. So the nice thing is, this entire domain is a surface. It is our in-plane surface. So I can create a new surface control. I'm going to name it best practice and all that, and call it max size. And I'm going to call this one, because I didn't name it before and I really should have. There we go. I'm going to call that far field refine. We're refining the field far away from the airfoil, and then we're going to be changing the max size. So for the max size, the surface we select is just the in-plane surface. That is everything we're simulating. The plane that we are simulating. And we can change the target size. We're going to also change this to 800%. So if I change this, we should see that these big cells become the same size as the ones further away. And we have a nice uniform field. The maximum cell size is like 0.32 meters. Okay, that's probably good for far away from the airfoil, but let's look nice and close to the airfoil. Well, a couple things jump out. We do have some reasonable fineness cells near the trail or near the leading edge, but we only have 2 prism layers. That's going to be a problem. We need more. We need to resolve what's going on in the boundary layer to a much greater extent. So let's just change overall how many prism layers we have. We only have a prism layer on the airfoil, so we don't need to do a custom control for this. We can just change the prism layer everywhere. So if I click on the folder, Prism Layer Controls, we have an option down here, Number of Prism Layers. I'm going to say 16. And then the rest of these are a little bit more advanced controls. But I'm going to turn down the thickness a little bit as well to 40%. There we go. That looks more reasonable. So the couple things to keep an eye out for when you're looking at prism layers is you don't want immense changes in size from the last layer of the prism layer to the adjacent core mesh. So this sort of transition is a little bit unusual because the prism layer cell is larger than the adjacent cell. That's probably fine, because this behavior is going to reverse later on, where you have the prism layer cell and then you have the adjacent cell, and the adjacent cell is actually considerably larger now. You probably want to keep that to a ratio of like 2 to 3 to 4 maybe. You don't want... Let me show you what you don't want. This would be bad. You have a cell that's itty bitty, this thin, and then boom, really big cell. That would be bad. It might even still be able to deal with it. Like out here, it would actually be okay, but in a lot of places, it's going to be somewhat wrong. So we're going to go back to 40%. Okay. Now the other thing is over here at the trailing edge. Oh boy, is that tessellated to hell and gone. Like, this is supposed to be a round edge, and it's like it's got like 3 facets to it. So we need to do something about that. The problem is this is a 2mm radius curve that it can use a minimum cell size of 2 millimeters on. So we can change the minimum cell size here. So we can create a new control. I'm going to call it TE refine, or trailing edge refine. And we can change things like the minimum cell size. And we can change it to, instead of being 10%, instead of being 5%, we can change it to 1%. Like a fifth of a millimeter is going to be the minimum size back here. And we need to select those surfaces that are the trailing edge of the airfoil. We can actually click on them and they're highlighted. And we can see that, oh yeah, it recognizes that those are the trailing edge of the airfoil, and it will make cells that are far smaller. Now, it's still doing some weirdness out here a little bit. That's almost unavoidable. But what we can also try and do is shorten up the prism layers. Let's see if we can change the prism layer total thickness to be like 20%. So the prism layer gets a little bit thinner right at the trailing edge. There we go. That's better, at least. It's not great, but it's better. And also, what's the other thing? So the big thing is these cells are kind of a little bit awkward to deal with here. So let's see if we can make the prism layer even thinner. And see how that changes it. Okay, not ideal, but probably serviceable. And last but not least, at 0 degrees angle of attack, this thing isn't going to generate a wake, but we're not just testing it at 0 degrees. We need to test over a range of angles. So we are going to want to add a wake refinement. So that is a surface control. We are going to refine a volume in space behind a surface, behind our airfoil. We are going to enable wake refinement. We get some values to mess with here. So under wake refinement, we turned on wake refinement. We have some values. We have a folder called wake refinement. And it's going to say it's going to sweep 10 meters behind the airfoil with a 0-degree angle cone, 0 radian cone, in the x direction. So it's going to go in the x direction, 10 meters, just projecting this airfoil, and make the cells smaller in that space. We're actually going to sweep this out by 3 degrees. So it's going to have a small, relatively small inclination change. And we're going to make the cell size 50%. We're also going to have the cells grow slower, match what we did previously. So again, we're basically saying take the region in space behind this airfoil that is shaped like a 3-degree half-angle cone in the x direction, 10 meters long. Make the cells a maximum of 50% of base size. We can see that it indeed did that. And honestly, we might want to do slightly more than 3 degrees. I'm going to go with like 5 degrees. And I'm going to tell it 15 meters instead of 10. We're still not up to that many cells. We haven't even broken 100,000. We're probably about to break 100,000, but not by much. There we go, that's a little bit better. And what we're going to do here is, I think, honestly, that's a pretty reasonable mesh for the most part. We need to set our free stream conditions. So I'm not going to be terribly picky about this. Well, actually, we also need to set our physics condition. So let's select the physics we're going to use. Steady, physics, gas, because it's going to be air. Segregated flow, because it's going to be pretty incompressible. We will select ideal gas just in case, but it's going to be pretty incompressible. Turbulent flow, because flow will eventually separate. And we're going to go with K omega turbulence. Generally, it's going to be better for things where boundary layer separation needs to be predicted accurately. We don't need any of these other fancy models, because we're not doing anything that really involves any of them. Close. And we're going to call this air. So this is our air physics model. By default, it is using air. You can see under models, under gas, it has the properties for air selected. If we were using a different gas, we could change it there. But now we can actually give these boundaries properties. So 300 Kelvin, that's fine for an inlet temperature. That's going to be a density of about 1.18. Velocity, this is a 2-meter chord. So if we wanted a Reynolds number of 200,000, or to make matters a little bit more round, let's go with 240,000. That's, give 1 point that, 10, only about 5 meters a second, I think, gets us a Reynolds number of 200,000. We could go to a Reynolds number of 50, and that would be 2 million, I think. Or a million would be 25, I think. So we'll go with 25 meters per second. 55-ish miles an hour, give or take. And call it good. And we'll see what this looks like. So let's measure a couple of things here before we even simulate anything. Create some reports. Let's measure forces. First, lift. Lift will be in the positive y direction. So 0, 1, 0. Pressure and shear forces. And we are going to measure forces on the airfoil surfaces. The airfoil and the trailing edge of the airfoil. That is lift. We can also measure force drag. I won't be quite setting up all the reports that I'm asking you to for the sake of time, but I'm setting up some of the more important ones. So surface of the airfoil in the X direction will indeed be drag. Good. Let's also set up the moment. So we want this to be a pitching moment about, let's see here, nose up is positive. So we actually want this to be a pitching moment about negative Z. We don't want the origin at 0, 0, 0. We want the origin at the quarter chord. So we want the origin at 0.5 space 0 space 0. And we want the moment on our airfoil. Okay, we have lift, drag, pitching moment. We can also create force coefficients. Yeah, so we want to measure force in the y direction. So 0 space 1 space 0. Our density is not 1. It's about 1.18 at these temperatures and pressures. Reference velocity, 25 meters per second. Area, 2 square meters, because we have a chord. Well, actually, technically it's 0.05005. Because we have a 2 and change meter chord by, it's a 2D simulation, so 2.005 times 1. Again, this keeps on popping up off screen. I apologize. We select the airfoil to measure these forces on. Force coefficient. Rename C D. We have 1.18, 25 meters per second, 2.005, and we again select the trailing edge of the airfoil, or the entire surface of the airfoil, excuse me. Last but not least, we have our moment coefficient. Similar thing, but we have a couple of additional terms. Again, we want to measure moment about negative Z from the quarter chord. 0.5 space 0 space 0, 1.18, 25, and 2.005. But we also have a reference radius. This is just the chord in this case. So 2.005, and we select surface of our airfoil again. We're looking at forces on the surface of our airfoil. So this is, oh, I hit refresh, not rename. CM C/4. So coefficient moment about the quarter chord. Now we can create plots for all these. Monitor and plot from report, and I'm going to create a plot for each and every one of these. I am also going to create a combined plot for CL and CD. So we can see both on the same plot. I'm going to click save. I honestly should have clicked save a long time ago in case this crashed on me. But there you go. And we're going to see if it yells at me. Click run. Ah, it's not yelling at me. We see the residuals generally trending down. So we can see our CL and CD changing, and they are starting to converge. I don't know if you can hear it in the background of me talking, but the computer fan has decided to kick on and start doing its thing, trying to keep this cool. And unsurprisingly, the CPU is having a hard time of it at the moment. Not quite all of it, but almost all of it. So this is getting kind of close to converged. You can see this is asymptotically converging, but it's not quite done by 1,000 iterations, which is the default stopping criteria. I'm going to turn that off and let it keep on running. And theoretically, eventually this should taper off and stop walking up, and it should just be oscillating around a pretty constant value. And honestly, we might be there. Let's see. Let's look at just coefficient lift. If it is walking up, it's doing it very slowly. So if we're being perfectly accurate, what you'd want to do is look for where this curve inflects. But this, in all likelihood, because of you can see how small the magnitude of change here is, that is very flat. So that's fine. Like honestly, we probably could have called this back at iteration 1600. I would have been comfortable calling it there. So this is converged. Let's take a look at the residuals just to make sure. Yep, all our residuals converge, and honestly, like our properties were pretty much converged by back here by about iteration 1000. So shortly after, not quite when the residuals became constant, but shortly thereafter is when the properties were constant. Again, I would have been comfortable calling this conversion about 1600 iterations. Let's take a look at what the pressure and velocity looks like really fast. So we're going to open up a scalar scene. We're going to look at static pressure. Now, this actually isn't ideal because we can see this bubble of static pressure kind of extends upstream far enough where it's kind of interacting, but let me... Yeah, realistically, I'd like that outlet to be a little bit further because you don't want any of this to be interacting with the boundaries in an ideal world. So we might need to fix that. And then if we look at the vector scene, if I change this to line integral convolution, we have a fairly reasonable looking flow field. This is a nice low angle of attack. We have a stagnation point. We have a small stagnation point slash bubble here at the trailing edge. That's not unexpected due to the rounded trailing edge there. So let's do a couple things here. First, I want to demonstrate the fact that we can just remesh this without resetting the simulation. Let's click on our error block, and we're going to go another 5 meters upstream. So I'm going to change this leading edge of the block from -10 to -15 and remesh. And hey, it's remeshed, and we did not need to reset the simulation. We can just hit run, and it will keep on going from here. You can see there's a hiccup in the results. They actually did change slightly. Very slightly. Due to that change in the mesh. Due to having that larger upstream run-up area. Whether it's a significant change or not, that depends on the precision to which you are looking. I would argue it's probably not, because we went from, let's see here, 0.3 or 37085 to about 371. So it went up by like, what is that, 0.0005 CL? That's probably not enough to be worthy of note. But the big thing is we are able to remesh with the simulation not being reset. I'm going to click save, and we're going to do one other thing and just demonstrate the fact that we can change the angle of attack. If I come up here to the rotate, and I'm going to say 6 degrees. Well, all of these need updating now. If I just tell it to rerun the automated mesh, it will redo everything that it needs to do in order to run the automated mesh again. Okay, so the mesh should be just about updated. Let's take a look at this, and we should see this airfoil is now canted at 6 degrees. It definitely has a noticeable angle of attack now. And let's tell it to keep on running. And take a look at what the pressure scene looks like. Taking a little bit of time to figure out what's going on here, but it's definitely working on figuring out the new pressure field around this thing. Also the velocity field. You can see kind of some of the effects propagating downstream from where it was trying to figure this out. And it is still changing a little bit. Our residuals have not reconverged. They're all coming down, incidentally, which is a little bit interesting. Let's take a look at our CL/CD plots. Well, our CL's gone up quite a lot, no surprise. It's not converged yet. This is still changing a noticeable amount, but it's getting close. CD looks like it's probably already pretty much converged. A little bit hard to tell, but... Okay. That looks pretty converged to me. Lift, drag, where are our pitching moments? Hey look, we have a negative 0.1-ish, slightly less pitching moment. That's pretty much what we expect for this sort of airfoil. And incidentally, it has changed a little bit, but only a little bit, with angle of attack. It went from negative 0.091092 to negative 0.087, changed by 0.006 or 005, or 4, depending how you want to count it. So that agrees with what we'd expect. We expect relatively minimal moment change about the quarter chord for an airfoil in a not stalled regime. So we can, and we have the residuals. They do indeed look converged now. So they were converged probably right about 4200-ish. This is oscillating a little bit, but this is kind of down in numerical precision territory. This weird step function going on here. But this is pretty solidly converged. So that's an example, we've gone through everything top to bottom of taking an airfoil. Again, not the airfoil you have, not the size airfoil you have, but an airfoil. Putting it in a domain, meshing it, setting up the physics, setting up the boundary conditions, running it at more than one angle of attack, and changing the mesh dynamically without resetting the simulation. Now, if you do get a floating point error, what you can do here is come up here to solution and say clear solution, and then change your mesh or improve your mesh or find out where the problem is in order to make it better. And usually it's going to be a mesh problem if you see a floating point error. But if you see a floating point error, come up here, say clear solution, and try again after changing some stuff. If you see a error code 8, that just means it couldn't get a license and something went wrong with opening the file. But other than that, I think that should be it. So I'm going to stop this video here and upload it, and we will talk more in class.